Good morning. Hope you're wide awake because we're taking a deep dive into the layer 1 today. Woohoo! So our topic is submarine systems technology trends and coping with relentless demand. And we all know that we are the cause of that relentless demand. So we have as our first speaker David Ross. And David has served as in the international communication industry since 1970, and he started at Bell Labs with the development of technology for undersea communication system. So he has a 30-year career into managerial positions at Bell Labs, AT&T, and Tyco. And at the end of that 30-year, he started his own company, the David Ross Group. So for the past 10 years, he's been leading his company, his consulting company, into providing technical, commercial, and managerial services for building subsea systems. And his firm's activity has been involved into 20 undersea cable networks. So we have a real expert on our hands. So Mr. Ross received his bachelor's and his master's degree from the University of Michigan in Ann Arbor. So he's from this community, and he holds several patents, and he's a published author, and we invited him as a speaker. So we're very thrilled to have him, and please welcome him to our NANOG panel.
I'm not David Ross. I'm just going to present our second speaker, that is Per Hansen, a fellow Dane of mine, actually, even though he has lived in the US the past 20 years. Per also started out at Bell Labs, but is currently the Senior Director at Submarine Solution at Sienna, and he's focused on the network demands needs for the submarine cable operators. He joined Sienna in September 2008 from ADVA Optical Networking, and prior to that, in 2004, he was one of the 5 funding professionals of Futurus Incorporated. That was an early innovator of dynamical optical network solutions. So we're very happy to also have Per here, and I will leave the microphone for David now. Yes, your talk here. And then you got to start the control out. Yes.
Okay. Well, thank you and good morning. This talk might be seen as a follow-on to a talk that one of my colleagues, Samia Bassoon, gave for this group a couple of years ago. But it's going to be a very different talk because, while she talked about the technology itself and focused on the hardware, and you saw lots of pictures of electro-optical equipment and undersea repeaters and cable and ships and so forth and so on, I'm going to talk more about the commercial implications, and I'm going to leave the technology talk to Per. But the commerce and the technology are very closely linked, and I'm sure that all of you are struggling with each aspect of this thing, and you can read about me at your leisure. But I'm going to start where we start all talks, where we start all business plans, where we start all endeavors in the world today, and that is with traffic. Okay, when I was learning traffic engineering at AT&T, the motto was, it all starts with traffic. And I'm sure that's true in your networks today as well as everything we do today. And today what we're grappling with more than ever is relentless, enormous, continual growth. And back in the days when we were tracking voice traffic, and we were just talking about this today at breakfast, everything was very easy, it was very predictable, there were very long planning cycles. To a certain extent, we controlled the timing of when things evolved. Today we don't have that control, and most of us are struggling to keep up with the development of the technology and with the provision of new systems. And network operators and network owners are struggling with decisions about how to invest their money. Do they upgrade the facilities they have, or do they build new ones? Those are the kinds of questions we're going to be looking at today. But the thing that drives all of it, and this is a slide that I borrowed from Tim Strong at Telegeography, with whom we do a lot of work, and they're the primary source for international traffic data. And what it shows is that growth has continued unabated for the past 3 years, but if you went back 3 years and 3 years before that and a decade before that and 2 decades before that, you'd see the same kind of pattern, just not quite as pronounced. Continual growth, and in fact, even in a worldwide economic downturn, demand grew all over the world at a rate that not only kept pace with the period before the economic downturn, but in fact accelerated. And this is the world we live in. Worldwide, traffic is growing at a rate of about 60% per year. And the reaction to that, of course, is to build more capacity. And as is stated on the slide here, when it's doubling roughly every 18 months to 24 months, the implication of that is that more capacity is now added in a single year than the total that was in service 2 years before. So in 2009, in the international plant, we added about 10 terabits of capacity, which is more than what we had in service in 2007. And we're seeing this in every region of the world. Not too long ago, this was confined to a couple of the major markets. But as we've been spending more of our time connecting places that had never been connected, and for my company, that's most of our endeavor, what we're finding is that every place we go, the Middle East, Eastern Europe, South Asia, Africa, they're all growing at phenomenal rates. And what you can see here is that in many of these developing areas, the rate of growth is well over 100% per year. And in fact, in almost every one of these regions, what you saw was that during the past year, the rate of growth was even higher than the average of the previous 3 years. So when Tim Strong presented this slide, it had the title, Recession? What recession? And the reaction to that in constructing new networks and in adding new capacity has been a continual upward growth in the amount of capacity that's implemented worldwide. And it's gone on, this just summarizes what's gone on over the past decade in the major ocean basins. And you can see here that there is no place on Earth where there has not been very significant growth. Some of this growth is from adding new networks, particularly in places that were underserved or not connected before. And some of it, for example, in the Atlantic, has all been with upgrades to existing facilities. And this is the same kind of thing I know that's going on in the North American networks. It's the same thing that you're dealing with here. Very large infrastructure built some time ago, continually upgraded, to the point where we're reaching the breaking point in a lot of these heavily developed networks. And I'm going to focus on the Atlantic now. In the Atlantic, we have the most competitive capacity market on Earth, and I'm talking strictly in the international forum here. Because we have 13 transoceanic cable spans that were built on that one route between Europe and North America in a 5-year period between 1998 and 2003. It was an overbuild. Many of those companies went bankrupt and so forth and so on. You know that whole scenario. But the result of that is that there have been no new systems built in that basin for the past 7 years. In fact, there was only one built as recently as 2003, and all the rest were built pretty much before 2000. So all of the growth has been in upgrades. All of those systems are being upgraded well beyond their initial design capacity. Over 10 terabits of upgrades have been put into that basin in that period on systems that were by and large developed for a third or two-thirds of a terabit. And the question continually arises, when will operators build new systems? And the question is an economic one, as well as a technological one, and we'll cover both sides of that. Now, the thing that's allowed those continual upgrades is that the technology for upgrades has continued to advance, and I know that you're reaping the benefit of that very much in the terrestrial networks in North America, but it's in the international business, it's nowhere seen more than in the Atlantic. And I've shown here what, for those of you who attend technology development conferences, is a familiar curve, that of the development of capacity on a single fiber in research labs over the past decade. And what you see is two things. First, there has been continual growth in the ability to put capacity on a single fiber. But if you look at the rate of that growth over the past 10 years, it's been considerably less than the rate of growth of the demand itself, the implication being that many new systems need to be built. The other thing is that while upgrades have continually been done, there's been a lag in the application of the newer technologies in the undersea world. For example, there are no 40 gigabit systems installed anywhere in the world undersea. There are some 40 gigabit upgrades, and I've just shown the latest upgrade result in the Atlantic, putting 3 terabits on a single fiber in the most recent undersea system implemented in the Atlantic. So that's sort of the high water mark. And you can see that it lags the research result by several years. That's what's happening in the undersea world today. It's become a very conservative place to invest. We're still building, our company's still out there building 10 gigabit systems all over the world. And we're just getting RFPs for the first 40 gigabit systems to be implemented undersea just this year. And with that technology advance, the ultimate capacity that's estimated for the systems that have been installed in the Atlantic has continued to grow. Now, this is just an estimate. This isn't to say that everybody will go out and tear out their 10 gigabit plant and replace it with 40, but if they did, according to the vendors who produced those systems, this is the type of capacity that could be realized. A few years ago, we thought it was about 25 terabits, and a year or so ago, we thought it was 50 terabits, and today the estimate is more like 100 terabits. But the technologists who developed those systems are telling us that's sort of the end of the line. We can't push another generation onto those systems, and we'll see what Per has to say about that, but that's what we're hearing from the folks who developed the systems that are already in there. Regardless of whether there are further upgrades or not, the fact that the demand is growing so much faster than the ability of the technology to meet it means that there will be a need for new systems. It's only a question of exactly when. And so we've shown here for various supposed growth rates in the Atlantic when those new systems might be needed. And this is just looking at the basin as a whole, not any particular system. This is when the basin is going to run out of capacity. It'll be sometime, most likely, given the current growth rate, in the 2014 to 2015 area. And what that means is that some systems, some of the earlier systems or smaller systems that were deployed, are going to be running out of capability earlier than that, and they'll be moving to build new systems quite soon. Now, why would somebody build a new system if they could upgrade? Well, there are a number of reasons that people build systems in the first place, and it's not simply all about needing more capacity. But one obvious place, and the place that we've been focusing on, is when they're looking for more capacity than an upgrade can deliver. And quite a number of systems are going to be in that situation during the next few years. But they also might build a new system when they're seeking enhanced route diversity. And this has become a major issue in the undersea world, as whole countries are cut off when cables are cut. There's still a very sparse infrastructure in the international space today. Seeking lower latency. And just this past week, we in fact had the first company announce that they're going to build a new system in the Atlantic that has made that announcement. The last time we heard that announcement was about 2001. Just this week, Hibernia announced that they'll be building a new system, and the goal will be reduced latency. They're being driven by large financial investors who are seeking to save a few milliseconds in the transatlantic transit. For an existing operator who's looking for more market share, somebody who sees an opportunity that if they build more, they can take more of the market. Or a carrier that doesn't have a footprint in the Atlantic today, deciding to move in and enter that market. And again, we have a timing opportunity right now when there's going to be a need for building new systems. And so people are circling around, and there's a lot of speculation about who might build these systems and when. Now, the reason that this is so controversial is that for a long time now, after the downturn in which prices for capacity fell precipitously, there's been a continual decrease in prices, and we know that you all deal with falling capacity prices. But it's been particularly pronounced in the Atlantic. And in fact, the capacity prices for transatlantic transit are the lowest in the world. And operators have argued for many years that they can barely afford a new upgrade channel for their system for what they can sell the capacity for. So they couldn't fathom how they would come up with the capital investment for a new undersea system. And these systems are very capital intensive. The average upgrade costs tens of millions of dollars to upgrade some number of channels that can serve them for a few years. It can be done incrementally. But if you're building a new system, you need to do it all at once. You need to invest up front. And in the Atlantic, the investment for a single strand across the Atlantic is on the order of $200 million. So it's a big decision. And it's being worked against ever-falling prices. So is it feasible? And the answer is yes. It's all in the numbers. If you have the situation that we have today, where demand is growing faster than prices are falling, which means that actual revenue is increasing, and if the demand is high enough such that for any given operator, the demand times the market price times their market share compares favorably with the system costs over a period of years, they can afford to build. And it's just now becoming true that we're breaking even on that calculation. So if the present trends continue, and they have been pretty consistent over the past couple of decades, we're going to see demand in the Atlantic high enough that it's going to be feasible to build for an operator who can capture 10, 15, 20% of the market. And there are a number of big operators in the Atlantic who have that kind of capacity today, and this is capturing just the incremental market, just the new growth. So in conclusion, the demand growth that we're seeing throughout the world is requiring a continual investment in new capacity. That's what keeps most of us going, keeps our company alive. We're all happy about that. Technology has made it possible to upgrade systems much further than their original design capacity, which has kind of provided a buffer and allowed the industry to keep moving forward while getting into position to build new systems. And despite the fact that all of the systems out there are being upgraded as fast as anyone can do it, it's still necessary to build new systems for a variety of reasons. And while most of our activity in the world has been connecting the unconnected over the past few years, we're going to see a turn in the next few years to rebuilding the places that we built in the late 90s. It's going to be feasible even in the most competitive and the most low-price markets. So the answer in general to cope with demand growth is not to upgrade or build, it's to upgrade and build. Each has its own time, each has its own place, and we're in a place now where people who've been upgrading for as much as a decade have to face a hard decision about building a new system. So with that, I'll turn the microphone over to Per, who will tell you about the technological advances that are driving that capability.
There you go. Sorry about that.
Thank you. So thank you for including me on the panel here. I think this is a very interesting topic, and clearly for us who do our business in this area. So I'll try and follow up from David and talk about some of the challenges that exist when you are trying to add more capacity, in particular, from our perspective, how you add more capacity on existing cables. David did a great job of presenting to you how the demand is really growing worldwide, and this here is my own little picture of that. If you look at the transatlantic that David talked about, we are looking to have to increase the capacity by about 24 terabit per second over the next 3 years, and that compares to the upgrade David mentioned of 10 terabit over the last about 10 years. Right, so there's a huge job in front of us to do that. Now, the transatlantic is one area that excels in terms of total capacity. You can also look at the areas of the world where there may be more growth, although they're starting from a lower starting point. In Asia, for example, many countries are looking to add more than 100% capacity each year for the next 3 years, right? So the growth in some of these areas are just tremendous. When we are trying to design solutions for how do you get more bits across these cables, you obviously have to contend with a situation of a long cable that's deployed under the water. You can't go in and tweak things, so you have a pretty firm starting point or playground that you have to play within. But then beyond that is how many bits can you get across a certain spectrum. Each cable has a certain spectrum that is enabled by the amplifiers on that cable, and our job is to try and utilize that the best we can. So the way that people have gone about increasing capacity in the past has been using TDM. So essentially you just send the bits faster and you get more bits across. But there's a number of problems with that now that we are reaching into the speeds of 40 gig and 100 gig and probably above that. A lot of these components gets very expensive. If you're on the forefront of things, you have to use components that may not be as mature as the ones you would like to have, especially when they're deployed on an infrastructure as expensive as the submarine cable. The performance that you can get at 40 and 10 is not as good as at 40 and 100 is not as good as it was at 10 gigabit, and that has design implications when you're trying to deploy this on a cable that was really designed for 10 gig, but now you want to run it at 40 or 100. The point number 3 that I have here is the incompatibility with some existing cables. That actually goes more for the terrestrial side. On the terrestrial side, you have ROADMs and other filter devices that define a wavelength grid that you have to be on. In the submarine space, we don't have to deal with that. Typically, we have much more freedom. And as I'll show you later, I think that is going to be our path to even higher capacities in the future. We have increased sensitivity to chromatic dispersion. So chromatic dispersion is the effect in fibers that makes different colors of light propagate at different times or different speeds, which means that if you have a bit that is sent from one coast to the other, the forefront of that bit and the tail of that bit is going to arrive at different times just because they travel at different speeds. And that's a huge problem when you go to 40 gig and 100 gig. The last one I'm mentioning here is polarization mode dispersion. Think about the chromatic dispersion, but now it depends on how the field is evolving inside the fibers. The fibers are not perfectly round, and that means some light will see different delays depending on how the path evolves as it's propagating, and now you have a mirror image that arrives at a different time. That again creates a lot of problems as you go to shorter bits. So there are many ways you can think about upgrading capacity. One of them is, as you can see to the right here, just using the speed of the bit. Make the eye pattern shorter, if you will. Press more bits into the same time slot. But there's a lot of other technologies that you can use as well. If we go around clockwise here, you can think about having subcarrier multiplexing. As we're advancing the technology for optical communication, we're actually starting to use a lot of the technologies that were developed years and years ago for radio communication. We can now control that in the optical domain with the frequency that we're working with there. Moving on further, polarization. We can actually use that polarization to send signals in both of these polarizations. And with advanced receiver technology, we will choose to receive just the one we want to receive that carries one signal, and we can use the other one for additional capacity, effectively doubling the capacity from that effect. And then the last one that I'll spend more time discussing here is more advanced encoding technologies. In the past, we have focused a lot on simply turning light on and off very quickly. If there's no light, it's a 0. If there's light, there's a 1. And we're moving way beyond that right now, not just encoding intensity, but also encoding the phase. So we're actually looking at the complex field of the optical wave that is being propagated across the fiber. Now, a lot of these things were just not doable 10 years ago, and what has really changed this field is DSPs. Over the last 10 years, DSPs have just evolved in phenomenal ways, and most of what I'm discussing here is enabled entirely through DSPs. So I want to just take one step back and just discuss encoding technologies a little bit. I think it's important for appreciating how these technologies can help you in the future. So to the left, you see the on-off keying. So basically, that's the lights on for a 1, lights off for a 0. And you can see the electrical field of the optical signal shown in that chart just below it. A 1 has a real component, no imaginary component, really, because we're just working with intensity. And the 0 is the 0, right, the 0.0. And you can see the eye diagram that you see below. This is shown against time. There's some that comes in at 0. There's some that comes in at 1, at the 1 level. The next step that one can take is to use BPSK, binary phase shift coding. And instead of encoding it now as light on-off, we encode it in the complex domain. So a 1 is shown here as having both a real and an imaginary component to that field vector. And the 0 has another constellation, or is another point in this constellation. None of them actually have 0 intensity ever. And if you look at the chart below, you'll see they actually have the same intensity always, and the difference between them is just the phase, right? You go around that chart. We can extend this further. QPSK does the same thing. It just has 4 states rather than 2, and that means that for every symbol that we transmit, we now transmit 2 bits, right? You can have a 1.1, a 0.1, and so forth, and that's a method for packing more data into a certain symbol rate that we are transmitting. Here are some charts that help us understand how we can now build up to higher capacities. So if you look at the upper right, you will see a BPSK chart. The upper clouds, where you can see just one round sphere of dots, that's essentially what a normal receiver sees as the signal comes in. You can't figure out what is 0s and what is 1s. That is sent into a DSP, and that will sort out the different phases of the signal, and it will decode it back so that you get your 0s and your 1s out. And below those red and blue clouds, you have 2 distinct clouds, one for 0s and one for 1s. And the same picture repeats itself in QPSK, except after the DSP, now you have 4 little clouds that each corresponds to pairs of bits. That means that if we're using QPSK over BPSK, we get a doubling of the number of bits per symbol. We can do polarization multiplexing, as I talked about before. That can give us another factor of 2. Each polarization carries an independent signal. So now we're up to a factor of 4. And then you can do subcarrier multiplexing. You can pack these spectrums very closely together within a wavelength, and you can get another factor of 2. So now we have a factor of 8. And if you're transmitting a 100 gigabit signal, you can apply this factor of 8, and we can design equipment that propagates as if it was really a 12.5 gigabit signal, very similar to the 10 that cables operate with today, and we can get the same propagation characteristics out of it. The key to receiving signals that are encoded with phase modulation is coherent detection. And coherent detection is very critical for these benefits. what is important to understand about that is that your normal detection detects light, whether it's on and off, and it's called a square law detection because you receive light, it beats with itself, and you get an electrical field out of that, and that's where you have your squaring. In coherent detection, it's linear, and that means that where we used to do dispersion compensation in the optical domain, that's why you have big spools sitting in the landing sites to compensate for the dispersion. Since this is a linear translation from the optical to the electrical domain, we can actually do all of these compensations in the electrical domain. And dispersion compensation is very simple in the electrical domain. It's a cheap filter. Now, we like to make it a little more than a cheap filter because we want this to acquire the optimum adjustment, apply the exact correct filtering so that you have the optimum transmission. And you can turn that around and say, well, when we can do that, we can make this very automated. So instead of having to go out and engineer, figure out how many spools of fiber do you have to install, this little card using coherent detection will go in and say, oh, okay, you have so much dispersion across this link, I'm dialing the filter in, and now you're optimally compensated. With fibers, you do engineering, you put lots of fiber that you also pay for, of course, into the landing station, and you're still not optimal. You're within a window, an acceptable window, and you have to set a margin aside for that. With coherent detection, you can optimally compensate, and you don't need to set a margin aside. So there's a whole range of challenges that signals encounter as they propagate that we can address in this way. The same goes for polarization mode dispersion. We can take that out. Various nonlinear phenomena can be minimized using this. Overall, there's a lot of things that you can do automated once it's in the electrical domain. We're even trying to do it in the optical domain if it's possible. Sometimes it is, but typically it's very expensive. What it also gives you is that since it corrects for these deficiencies, it'll tell you how big they are, right? So in every transponder now you have essentially a performance monitor that'll sit and say, well, I had to temporarily dial up dispersion, and you can go in and see that in a log. And that tells you, well, somebody fiddled with this cable, right? Because there was a change over some minutes, and maybe there was some submarine out there that found a cable or whatever, or some fishermen found it. You can see that in the trace because it had to change the compensation. And you can actually get a readout of what happened in the real optical domain as low as you can get in the stack. So I wanted to call out some particular features that you get from coherent detection, phase modulation and coherent detection that is interesting for submarine cables. Generally, these launch powers at very low launch powers. It's a function of the modulation scheme that you do that. It means that you have to make good receivers, and we can do that. It also means since they're low powers, they're friendly neighbors for everybody else on the cable. Right? That means we can pack them very closely together because they don't instigate a lot of nonlinearities that will create problems for its neighboring channel. So that's a key for us to be able to pack these channels very closely together and get to higher densities. It also, since we don't have to launch a lot of power, we can sneak our way into systems in various ways. Almost every system has a monitor port where you can go put a spectrum analyzer on and see what spectrum comes out of it. Even if that's a low ratio tap, it's enough for us to put a coherent signal on there. And in many cases, these upgrades are done through these monitoring ports, and then we just provide another monitoring port in replacement for the one we're using. Right. Coherent detection and phase modulation is amenable to a wide range of dispersion maps. One of the situations that we run into when we are trying to upgrade existing cables is that you have no effect over the cable. We can't pull it up and put a dispersion compensator in midway if that would make things better. We just have to live with what's in the water. And since this operates at low power, it's relatively insensitive to dispersion. what is kind of a funny side effect of this is that the poorest performing channels with phase modulation is the one in the middle, because it has the most neighbors to interfere with it. And the ones on the ends of the spectrum are the ones that performs the best. If you look at the conventional TDM technology with the amplifiers that are in the field, the ones in the middle are typically the best because they get the best treatment by the amplifiers. And that means that this technology really kind of helps even you out some of the disadvantages that already exist on the cable. Receivers are adaptive, as I told you. Since you have a linear translation from the optical domain to the electrical domain, you can do a lot of things in the electrical domain, and the receivers can be made to adapt entirely to the signal. No manual adjustments, very easy to implement, no re-engineering of the systems. They continuously update themselves to run at the optimum operating point. And you can see that in the graph here. This is a graph that shows the Q, which is essentially the eye opening, right, the quality of the distinction between ones and zeros, as a function of time, and this here was recorded over 12 hours. The red line is where we get in trouble. The FEC can't correct for the errors. All submarine systems work with FEC to improve the performance, and you have to stay away from that line. In this case here, there's a standard deviation of 0.03 dB, very small variation considering that this is a signal that have just traveled thousands of kilometers. On a normal TDM signal, you will see the window, so plus minus 3 sigma is probably on the order of a dB. And you need to set margin aside to allow for that in a normal system. If you have an adapting receiver that constantly updates itself to the optimum, you actually don't need as much margin. This shows one example where some channels has been put on a system. This is actually showing 100 gigabit per second transmitted over a submarine cable that was 2,100 kilometers long. If you look to the right, you can see the one where there's an arrow pointing to it that says 100 gig. This is subcarrier multiplexing, so you see two little peaks in that. Each of them effectively contains 50 gigabit of information. And this is sandwiched in between a bunch of 40 gigs just to show that the effects of neighboring channels can be managed. And in this particular case for this cable here, it was estimated that this could actually be upgraded to run 48 channels of 100 gig, spaced only 50 gigahertz apart, even if they're carrying 100 gigabit per second. I wanted to include some information about what has been done in the field. As David said, there's not been built a 40 gig system per se yet, but upgrades have started to take place. There's kind of an outline here from 2008 where commercial operations started with 40 gig wavelengths on one system with a 50 gigahertz spacing. You can see the second one is the trial I just described before, about 2,000 kilometers, 100 gig. You also have cables that have no repeaters in them. The Virgin Media deployment in 2009 is one cable that does 40 gig with commercial traffic. There's a 100 gig commercial deployment, not subsea, but terrestrial, using the exact same technology for 900 kilometers. That has been in commercial operation since last year. In essence, that's actually harder to do than the submarine because we couldn't go in and change the cable, but we had to go through all the ROADMs with all the filters, things that you don't have to deal with in a submarine cable. And then in 2010, more deployment on 40 gig as well as certification of 100 gigs upgrades. So depending on the particulars of your cable, the distances and so on, 40 gig does exist submarine today. 100 gig is around the corner. It's essentially a matter of the operators asking for it, right, and wanting to invest in them. So I'm probably running out of time, but I wanted to give you a little bit of a view towards the future. We think that with phase modulation, coherent detection, you're getting into a new realm of things of what you can do. And I'm very much hoping to prove David wrong in the sense that we can't keep up with upgrading cables. Ultimately, I think he's right, but we're going to try and starve it off as much as we can. We have 40 gigabit on a 50 gigahertz grid. We have 100 gig on a 50 gigahertz grid, and we can see our way up to doing much more than that, getting up towards 5 or 6 bits per hertz, which is the measure of density on a cable. Right? Today, 100 gig on a 50 gigahertz grid gives you 2 bits per hertz, and you really want to move that up because that's the ultimate capacity that you have on a cable. David talked about how cables have been upgraded already. There's some numbers here on a number of cables that have been deployed that today are running, 7, 8 times as much capacity as they were designed for originally. So capacity upgrades have taken place already. Let me just touch on one aspect before finishing up here, is that once you have a number of cables, it's also critical to use that assembly of cables in the most intelligent way. And you can do that by meshing them together, essentially switching your traffic around on the cable so that you can use the capacity the best. If you have only 2 cables across the Atlantic and one breaks, you need to be able to put all that traffic on the other cable. Now, if you have 6 crossings, like Verizon has in this example that they have described, if you have 20% extra capacity on all of them, if one of the cables break, you can reroute that to the 5 others. So you need to set much smaller fraction of your capacity aside for upgrades. So it's important to mesh your networks. And what we see happening right now is actually the large carrier meshing around the world. And in situations where you have a cable break, they will route the critical traffic, the latency-intensive traffic, on a neighboring cable that's okay, but capacity that's not so latency-intensive maybe goes around the other world, or around the other way around the world. Those are the type of networks that we are getting to today. And you will see the distinction between submarine and terrestrial cables will fade over time. It'll be one big network, but technologies will differ a little, but even that, a lot of it is coming together to create one global network. Thank you.
Okay. I've been asked to sort of kick off a discussion session on upgrades versus new builds with a suggestion for an analytical way to look at when one might choose to build rather than upgrading. And for those of you who aren't accustomed to looking at this kind of a diagram, this is a plot of the incremental cash flow, the investment and return on an undersea system. Now, this is a hypothetical. It doesn't represent any particular system. But what it shows you is the very large negative cash flow that takes place when you first build the system. And you have to spend all the money before you collect a dime in revenue. You have to build the whole thing. You can get to a cash flow positive, incremental cash flow positive situation very quickly when you turn the system on. And then slowly, because the demand continues to increase faster than the prices fall, typically the year over year, the revenue will increase until the system has been in service for a number of years. And then there are things that happen out here, and this is where you start to encounter some very serious need for upgrades because the demand is growing exponentially. And you have to choose between building, investing in those upgrades or building a new system. which will give you a lot more potential for new capacity. And among the things that happen out here are, number one, the prices continue to fall, and so you have a kind of a downturn there. You may run out of the ability to upgrade the system with the technology you have, and in that case you can't sell any new capacity, though you can continue to lease the capacity that you have, so the incremental revenue drops still further. And then there's a third factor that's more of a psychological thing, and that is that in a growing market where there is or will be investment in new systems, if your system is perceived to be old because it's been in there for several years, and these systems do have a finite design life, none of them have been in long enough to really test exactly how long they will live, but the fact is that once a system gets to be 7, 8, 9, 10 years old, if people have an alternative, they'll put their traffic on a new system. And so the market share of existing systems tends to drop. And so in the face of that sort of decreasing payoff of an existing system, this is where this region where I've sort of drawn the box, where all these different factors are coming into play, is where you need to make the decision. And unfortunately, because it takes so long to develop one of these systems, typical project runs 2 to 3 years, you have to start planning for this to happen before it actually happens. Now that's the trick, is deciding when to make the investment, when to start investigating it, when to actually start the development or pay for initial manufacturing, so that you can stave off a situation in which you're investing in something which basically is not going to generate much of a return. So again, that's sort of the commercial view, and we'll work that against the technological future and perhaps generate some discussion.
Thank you, David. Thank you, Per. Do we have questions from the audience? We have 3 or 4 minutes, I believe.
Tom Zeller, Indiana University in Air and AC. On one slide you were talking about performance being worse at higher speeds, and it showed 70% loss or something at 10 gigs, and at 40, and 90% loss at 100. And what is that loss exactly?
Yeah, so does this, okay, it'll work. So the reference that was made there is to the simple fact that to receive a bit, you essentially need the same energy, everything else equal in a receiver. So when you go from 10 gig to 40 gig, the average power that you need is 4 times as high, so that's the 6 dB disadvantage that you get. When you move from 10 gig to 100 gig, you need 10 times as much power because you have the same energy per bit but 10 times as many bits, and that gives you a 10 dB penalty overall. So that's what the reference is to.
Jeff Houston, APNIC. On terrestrial systems, the thermal effects on the cable system tend to abrade the cable against the sheathing to some extent, and you tend to get deterioration over time. To what extent in submarine systems do you see deterioration of the characteristics of the cable system over time? How stable are they, even without, fishermen trawling them? Are they incredibly stable, or over 10 or 15 years do they just degrade to the point where their characteristics are significantly different from the time they were put into service?
So probably, my guess is that David can add to this most likely as well. I'll give you my impression of that, is that the cables are, first of all, generally left alone in the sea, so that helps them. They do hang on ridges and so on and come in contact with rocks and so forth at the bottom, and currents can cause some disruption. I think typically the interruptions are more from very sudden events like earthquakes and so on that has distinct movements of of the plateaus and will rip cables. I'm not so familiar with the actual wear on the cables. Do you know, David?
Yeah, I think the situation, of course, the first undersea cables, fiber optic cables, were installed only in 1988, so there isn't a really long history with these things. But those first systems that were installed, their cables are still very much intact, and the sea bottom is actually quite a benign place. Cables tend to lie directly on the bottom. If the bottom is soft, they'll actually kind of bury themselves in the seabed, and they're really not disturbed by very much. As Per mentioned, there is a possibility of having suspensions or what have you, but we work very carefully to avoid those. And by and large, it pays off. You see, many of the very earliest systems are, in fact, if they've gone beyond their economic life and their original intention, they're being pulled up and redeployed in other places, seemingly without loss of performance.
So Jeff, the effect you're talking about is called strumming. It's when a cable kind of shifts back and forth on the bottom.
Strumming is one of the things
That's
that
right.
can happen.
But
yeah.
I'm a little surprised at some of the assertions with the lay process because, as you probably know, desktop studies are pretty extensive. When you go to deploy a cable, you actually do a fairly intensive study of the ocean bottom, and you try to do things like avoid volcanic or geological slide areas like we saw in the Asia Pac a few years ago when there was some earthquake activity in the nation and everything collapsed in on some of the cables. I'm not familiar with cables hanging over ridges as well. I think that the effect of the weight pulling on the cable would degrade it over time, and so I'd appreciate a reference point on that. But can you tell me how many wet systems are currently, how many 40 gig systems are wet right now, and how many might be in ITP? And ITP is intent to proceed. Basically, there's an agreement that the cable is going to go forward, negotiations continue. They provide some money to fund materials purchase, and then the deal gets sealed, and they go and deploy the cable.
I think as I said in my talk, there are no 40 gigabit systems in service right now, though there are a couple that have been contracted. Okay, and it's really just a very small number, and those are in production now and will probably be in service 2012, 2013.
And could you tell me who those systems are contracted with? Is it Huawei, Tyco, Sienna? I mean, who's got wet 40 gig gear under the water right now, or has signed a deal to put wet gear, to make their gear wet?
Well, let's talk about the distinction as Per brought out and as I tried to bring out. There are systems that have bits running at 40 gigabits where they've got 40 gigabit terminal equipment installed, yeah, and they're running on a wet plant that was designed for 10 gigabits.
Wet plants and
so
a kind of lag simulation, right?
So there are a number of those, and the new ones that have been contracted, Tyco is selling 40 gigabit plant, or TE Subcom as they call themselves now. Alcatel-Lucent is selling 40 gig plant. NEC, they all talk about having 40 gigabit product available. They're out there demonstrating via upgrades that the technology will work. They have laboratory demonstrations that they report.
I've seen all that.
But no one can point to a system that they've deployed that's in and working right now.
That's right. Sorry, I'm Martin Hannigan, the Iceland guy. Thanks.
Let me just add one comment to that, is that as we talk about, there's no cables that were designed to be a 40 gig cable yet, and that's what David is talking about. The list I put up was intended to show you that there are 40 gig wavelengths running undersea since 2008 carrying commercial traffic. So it's way beyond the stage of laboratory experiments and demos and things like that. The fact of the business is that you often don't get to deploy until you've done demos and trials, and often customers are more willing to let you share some of that information than actual deployments. And I would love to share names on some of these deployments, but we just are not allowed to.
Well, thank you, everyone. The undersea cable world is always fascinating to me. I always enjoy listening to these talks, even though I know I'm never going to lay an underwater fiber. And I'm just as glad that I'm not going to, actually.